Oh, I got it. Oh shit, I'm still showing. Fuck. Alright. I got it though, right? There we go. I guess that's yeah, that's high quality. Did it drop? No. Let's see how this scene looks. Yeah, cause now we're in 1080p, right? Let's do it. Let's go. Let's go. Let's go. Let's go. Bro, I wish I had a soundboard. I ought to buy one. That'd be sick. I gotta turn up my volume. Let's see. I think that sounds alright. Right? Loud enough? Could turn it up more. Are my headphones all the way up? I think so. Is this all the way up? Could turn it up more. Are my headphones all the way up? I think so. Is this all the way up? Nah, that's good. Now, another thing that kind of sounds like shit is my audio quality. So I'm gonna turn up the gain. Let's see how this sounds. I feel like that sounded better. I think I'm actually turning it down though, not up. I feel like that sounded better. I'm actually turning it down though, not up. That's a little too much. That sounds a lot nicer, right? That's a little too much. That sounds a lot nicer, right? Yeah, that's a little more clear. I think so, right? That's a high quality. Let's see some of my drawings. Just want to see if the words or if everything's easier to. Does that? I think that looks more clear. Bro, we're streaming at 1080p. That's beautiful. This is the first time that I've done it. Oh, it's. That's so good. That's so good. Let's see. I gotta see 1080p on YouTube also. Bro, we're streaming at 1080p. That's beautiful. Hell yeah. Hell yeah. Let me see. What's the difference? 720 and 1080. It's pretty noticeable when we're looking at the paper in my drawings because shit is just like, it's obviously so small. Okay, I'm sick of hearing myself though. Alright, cool. That's so fire. Oh, that's so good. Let's see. Picture in picture. I don't know what that means. Theater mode. Excuse me. Alright, cool. Oh, man, that's really sick. The sound quality's good, right? Hell yeah. Hell yeah. Alright, perhaps let's get into it now. Yeah, for sure. Get rid of all this so I don't lose the bit rate. Keep that open. Alright, well, let's do it. We're back into digital systems. We're IQ maxing with computer engineering. That's essentially what we're doing here. Dealing with digital circuits. I mean, that's literally the fundamentals to computer engineering, right? Although we're still looking at layers of abstraction, right? Because we're looking at like logical and OR gates, and then how those are utilized in like memory circuits, like flip flops and latches, right? But latches I don't think are really used at all anymore. Mostly flip flops. So we're gonna be looking at those. And I have some prep to do for an exam. Okay, I have an exam tomorrow for this class, so I'm going to learn some more of the content regarding latches and flip flops, and then we're going to put it into practice, and then we're going to work on the practice exam essentially. Although I think it's just a couple of questions, it's not much of a practice exam. Anyways, let's get into it. I have my flash drive plugged in. This has my content. Another thing that's very exciting is that I'm moving out of this apartment and into my new apartment, and finally they got in touch with me. It took a long time, and I was really uncertain about whether the apartment would still be available. But, you know, God willing, it is, and they said that I can come in to put down my security deposit. So, that's pretty fire. You know, I'm quite excited for it. I'm looking forward to getting into the place by myself because I stay here, and I share this apartment. So it's gonna be so sick. Might annoy the shit out of the neighbors. Who knows? Just kidding. That's not going to happen. Actually, I'm a great neighbor. I'm incredibly courteous, and you know, perhaps we can get together, have a just share a good time together. Break bread, have them over for dinner and things like that. Maybe, possibly, probably not. Maybe though. Okay. What chapter? Chapter 11. That is correct. Okay. Another thing I need to look at is the buffer. It's nothing crazy. Okay. I'm just gonna read the introduction straight at the bat. Might be boring as hell, but if you stick through, we're gonna do some cool stuff. All right. Sequential switching circuits have the property that the output depends not only on the present input, but also on the past sequence of inputs. In effect, these circuits must be able to remember something about the past history of the inputs in order to produce the present output. Latches and flip-flops are commonly used memory devices in sequential circuits. Basically, latches and flip-flops are memory devices which can assume one of two stable output states and which have one or more inputs that can cause the output state to change. Several common types of latches and flip-flops are described in this unit. In units 12 through 16, we will discuss the analysis and design of synchronous digital systems. In such systems, it is common practice to synchronize the operation of all flip-flops by common clock or pulse generator. Each of the flip-flops has a clock input, and the flip-flops can only change states in response to a clock pulse. The use of a clock to synchronize this operation of several flip-flops is illustrated in units 12 and 13. A memory element that has no clock input is often called a latch, and we will follow this practice. Morty, get in the fucking van, Morty. Alright, we will then reserve the term flip-flop to describe a memory device that changes its output in response to a clock input and not in response to a data input. Very well. How's the lighting here? Is it okay? Maybe it doesn't look bad. Let's see. I just gotta ensure the quality is high. Because of the quality.
How excited he is to who nobody ever says. We see
Bro, I had the desktop audio on. That's very annoying. Let's see, I just gotta make sure the quality's high. Yeah, it's a little dark. But what's that gonna really do for me? It's a little dark. No, I don't want to mess with that. I want to mess with this. Exposure. Not the zoom. Perhaps just the brightness. Nah, actually, it's pretty good how it was. I don't really like where this is going. I just kind of need more light where I am. But, you know, it really don't look bad, actually. Looks pretty good. Vislimit. We should definitely get something on the page, though. I definitely need something on the page. I am streaming. Everything's good. My BPS seems to be constant. That's fantastic. Okay. Alright, fuck it. Let's jump back into it. Okay. The switching circuits that we have studied so far have not had feedback connections. By feedback, we mean the output of one of the gates is connected back into the input of another gate in the circuit, so as to form a closed loop. In order to construct a switching circuit that has memory, such as a latch or flip-flop, we must introduce feedback in the circuit. For example, in the NOR gate circuit of figure 11.3a, the output of the second NOR gate is fed back into the input of the first NOR gate. Sequential circuits must contain feedback, but not all circuits with feedback are sequential. There are a few circuits containing feedback that are combinational. Indeed. Okay, wait, so is this the first and only time that it's gonna... Yeah, okay. Absolutely. So this is the introduction. So chapter 11. Let's, got a brand new pencil, so let's sharpen it, listen. Nice. Okay, so we got that. Let's go, what's getting blocked here? Is it that? It is that. Cool. Bro, are you fucking kidding me? Alright, sharpen it again. Try it this time. Alright. Chapter 11. Latches and flip-flops. Don't play with me, dog. Don't play with me, dumbass Nat. Get that shit out of here. Okay, latches and flip-flops. Flip-flops one? No, it's 2 words. There. Whatever. Latches, flip-flops. Okay. Alright, again, everything we read. So now we're just going to look at inverter with feedback. The first case of an inverter, and this is going to give insight into stability and unstable circuits. So, of course, we always want stability. And so let's kind of define what stability means. All right. So this is what we're looking at here. We just have an inverter. That's a symbol for an inverter. And we have this feedback loop. Okay. What else do we got? Just a variable x. Call it x. Okay. Now we're going to draw a graph for x, oscillation inverter output. Okay, draw a graph for x. And we just got some square waves. You know, whatever, something like that. Okay. And time. Of course. It's kind of a shitty square. Let me fix that. But, excuse me. I'm gonna go to the gym later, so comment what I should hit. Comment below. Let me pull up my. I actually can't read any. I actually can't read any of the chats because I don't have anything pulled up. Brother, I need to. At one point in time, I had the ability to have the chat displayed. And now I seem to have lost that ability. What the fuck? I can't maintain things. Although that was like, it's been a long time since I've done that. I'll figure that shit out later. Alright, let's continue to move forward because I got a test tomorrow. And I want 100. You know, I do good as it is now. But I want 100. Honestly, anything less than 100 is going to piss me off. And if you know me, then you know this. Alright, anything less than 100 is unacceptable. So... Alright, let's do this. In simple cases, we can analyze circuits with feedback by tracing signals through the circuit. For example, consider the circuit in figure 11a, which is right here. Consider this circuit. If at some instant of time the inverter input is 0, this 0 will propagate through the inverter and cause the output to become 1. Of course, that's just the basic properties of an inverter, right? So it's saying if we were to have a 0 here, then through inversion we have a 1. Now, look at the conflict that this causes. We'll continue to read, but just simply, you know, just by basic analysis and logical analysis, we can deduce that 1 doesn't equal 0, and now we have a conflict here. If this signal of 1 would continue to propagate around the loop, obviously there's a conflict. Okay, so we'll propagate through the inverter and cause the output to become 1 after the inverter delay. This 1 is fed back into the input. So after the I lost where I was. So after the propagation delay, the inverter output will become 0. When this 0 feeds back into the input, the output will again switch to 1. and so forth. The inverter output will continue to oscillate back and forth between 0 and 1 as shown in the figure. As shown in right here. As shown here, we have this oscillating phenomenon. Right, but that's not real, right? I'm just trying to think of like the applications of an actual like unstable. Maybe that's why they maybe that's why they call it that. That would make a lot of sense. We'll get back to that. I also have some crystals. Have some fucking crystals that I want to make some crystal oscillators from. That's actually incredibly exciting. I also have a Raspberry Pi, which I've worked with Arduino, but I've never worked with the Raspberry Pi, and I've heard very good things about it. It's incredibly powerful. And like, man, I want to make a product, brother. Like, I want to make a product. I want to start a business, do a startup, and all of that kind of good stuff. You know, I don't really know exactly what my application will be, but I'm gonna do it. All right. So stick with me. Subscribe, follow, whatever it is considered on the particular platform that you're on. But do it. Shoot a comment. Say what's up. Give me your mother's maiden name, your social security number. You know, whatever you want to do. Totally up to you though. Totally up to you. Let me just double check the quality. I just want to make sure everything's good, precise, and pristine. Yeah, it's looking great. Looking fantastic. Best I've ever seen, and I only seen it once. So, isn't that great? Nah. I don't know. The YouTube quality says 1080p, but it's not looking too good. Is it the lighting? Maybe I got too much light. Here, let me do one thing. Sorry, I hate the discontinuity due to me trying to fix things about the stream, but it's like I can't have a shit quality stream. That's too dark, right? That's too dark, right? I want to see it on YouTube or on Kick. I think Kick has less of a delay. No, that's better. At this point, it's not even the cameras though. For that. All right, cool. All right, we're back into it. Okay, so we have this oscillating phenomena. This one is fed back into the input, blah, 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 blah. An oscillator can be created using any odd number of inverters. The oscillator waveform has a high and low time. That is the sum of the propagation times of the inverters. For example, with n inverters and with all having the same delay, the oscillator waveform high time is n plus 1 divided by 2 times the high to low inverter propagation delay plus n minus 1 divided by 2 times the low to high inverter propagation delay. Okay, so an oscillator can be created using any odd number of inverters. An oscillator can be created. Whoops, I kind of fucked that up. Created using any odd number of inverters. How does that look? That's not bad, right? How does that look? It's kind of the real test when I start writing. An oscillator can be, okay, it's a oscillator can be created using any odd number of inverters. Hey, that's not too bad. All right. Okay, so very well, that's true. For example, with n inverters and with all having the same delay, the oscillator waveform high time is n plus 1 divided by 2 times the high to low inverter propagation delay plus n minus 1. I just want to understand what the fuck that's actually trying to say. N inverters and with all having the same delay. So let's kind of think about this. So with n inverters and constant delay. And inverters in constant delay. The oscillator waveform high time is oscillator waveform high time is high oscillator high time. Oscillator waveform high time is n plus 1 is n plus 1 over 2 times the high to low inverter propagation delay times the high to low inverter propagation delay. Inverter propagation delay plus n minus 1 over 2 times, I guess we'll say plus n minus 1 over 2 for real, times the low to high inverter propagation delay times the low to high low to high inverter propagation delay. I'm just gonna say propagation delay. Propagation delay. All right, that's not really vital information, but like you know, what I want to do is I want to get into the realm of making oscillators, oscillating circuits, and I don't know, like radio frequency and microwave applications and stuff. So that's really where my greatest interest lies. So I want to have the knowledge for the purpose of application. So let's look at a more stable circuit, right? Because to say unstable, that would be like the oscillating behavior. Okay, so let's have something that doesn't oscillate. All right, so we can do this by adding another inverter. Right, so it's as simple as that. Okay. Alright, so because if we have a 1 here, we'll have a 0 here. We still have a 0 here, then we have a 1 here, and we go back around the circuit. Motherfucker. We go 1 here, 0, 1 here, inverted, equals 0. We maintain the 0. It propagates to the second inverter. Inverted to 1 again, and this propagates around. And here we still have a value of 1. Okay, so therefore it is stable. Next, consider a feedback loop which has 2 inverters in it as shown in the figure. In this case, the circuit has 2 stable conditions, often referred to as stable states. If the input to the first inverter is 0, its output will be 1. Then the input to the second inverter will be 1 and its output will be 0. This 0 will feed back into the first inverter, but because this input is already 0, no change will occur. The circuit is then in a stable state, as shown in the figure. A second stable state of the circuit occurs when the input to the first inverter is 1 and the input to the second inverter is 0. The simple loop of 2 inverters lacks any external means of initializing the state to one of the stable states. The set reset latches in the next section have inputs for this initialization. Morty! Okay. Alright, so 11.2. Set reset latch. Or SR latch, but we'll write it out. Whoops. We'll write it out. Set reset latch. Baby girl, let me see it dance, let me see it twirl. Maintain that quality. Maintain that quality. We need some quality control up in this bitch, you know what I mean? Why am I still getting a shadow? Oh, it's the mic. I don't want to move the mic too far away. I think that looks alright though. Right. Yeah, it looks okay. Alright. Baby girl, let me see dance, let me see twirl. Just want to ensure the quality is okay. Man, these quality checks are gonna kill me, eh? Don't you think? Come on, motherfuckers. Join the stream and watch. Put your eyes on the stream. swear that ain't right. Alright, maybe I'm a little too vulgar. Maybe I'm a little too vulgar. Let me chill with the comments. Alright. Set reset latch. Very well. Alright. Fuck it. Fuck all that. I just want to keep that up. Let's go back to this. Okay. Set reset latch. We can construct a simple latch by introducing feedback into an OR gate circuit as seen in figure 11.3. I'll draw it out. As indicated, if the inputs are S equals R equals 0, the circuit can assume a stable state with Q equals 0. Wait, if the inputs are S equals R equals 0, the circuit can assume a stable state with Q equals 0 and P equals 1. Let's draw it out as we're learning about it. Yeah, so we can keep think about it and shit. I'll draw it right here. Alright, so that's pretty much what we're looking at. Set, reset, latch. Okay. If S equals R equals 0, the circuit can assume a stable state with Q equals 0 and P equals 1. Note that this is a stable condition of the circuit because P equals 1. Feeds into the second gate, forcing the output to be Q equals 0. And Q equals 0 feeds into the first gate, allowing its output to be 1. Now if we change S to 1, P will become 0. This is an unstable condition or state of the circuit because both the input and output of the second gate are 0. Therefore, Q will change to 1, leading to the stable state shown in figure 11.3b. Alright, okay. Back to 0, the circuit will not change state because Q equals 1 feeds back into the first gate, causing P to remain 0 as shown. Note that the inputs are, again, S equals R equals 0, but the outputs are different than those with which we started. Thus, the circuit has two different stable states for a given set of inputs. If we now change R to 1, Q will become 0, and P will then change back to 1, as seen in the figure. Okay, so, back to the beginning. Let's think about this again. S equals 0, R equals 0. 0... 0, right? S. Man, I kind of draw S's pretty bad, like, all the time. It's still pretty bad. R. Okay, so S equals, the circuit can assume a stable state with Q equals 0 and P equals 1. I mean, based on inference, right? We have a 0 here. Imagine we said that this was 0. Imagine we said Q equals 0. Then we'd have a 0 here. It's a NOR gate. So if we had 0, 0, this would be P equals 1. Indeed. Let's draw it again. Let's draw all of these scenarios so that I want to fully understand. Oh, I forgot to invert that. Don't forget our feedback loop. Got our feedback loop right there. Alright, cool. Again, SR will do some labels. Alright. So now our next scenario. forcing the output to be 0. Note that this is a stable condition of the circuit because P equals 1 feeds into the second gate, forcing the output to be Q equals 0, indeed. And Q equals 0 feeds into the first gate, allowing its output to be 1. Now if we change S to 1, P will become 0. This is an unstable condition or state of the circuit because both the inputs and output of the second gate are 0. Because both the inputs, so if we change S to 1, P will become 0. This is an unstable condition or state of the circuit because both the input and the output of the second gate are 0. Therefore, Q will change to 1, leading to the stable state shown in figure 11.3b. Right. So it's suggesting, now if we change S to 1. So it's suggesting now R is still 0. We change S to 1. We change S to 1. We know that P is currently 1. P is, do I have another color? This might be a bad idea, though. I don't know if it's going to bleed through. Oh, shit. I don't know. Let's see. So, yo, smells like shit. What? Oh. Like, it's not even a good, like, marker huff. You know what I mean? Like, it's not even good like that. It actually smells like diaper. Oof. Wonder why. Okay. Bro, ain't no way. I wonder where this thing has been. You know what I mean? Surely it hasn't, though. I mean, surely, right? I didn't do that. I didn't do that, but you know, it just kind of sits out here. So I don't know what any passerby could have done to it. You know, not here all the time. So. Okay, so the current state is 1, and the current state is 0. Okay. So with those being our current states, 1, 1 for NOR circuit would be 0. And so now P equals 0. Wait, that's not really the case though, because it's 1. That's not. Wait, did it change P first before it changed? P will become Q equals 0 and Q equals feeds into the first gate. Now if we change S to 1, P will become 0. Change S to 1, P will become 0. Why? Become 0. This is an unstable condition or state of the circuit because both the input and output of the second gate are Q will change to 1. So P changes based off of Q or S changing. Change S to 1 because P is here. P is currently 1. We currently have 1, 1, 1. P changes to, yeah, P will become 0. Yeah, okay. So 1, 1. P now equals 0. 0, 0. 0, 0 for a NOR gate is now 1. Yeah, Q now equals 1. Okay, very well. No, that makes a lot of sense. Are you following? Do you understand? Okay, so that actually makes a lot of sense. Bro, how do I not have anybody in here? That's crazy. Let's see. I don't understand the YouTube quality. Because nah, that's not it, bro. Why is the quality like that? It's bad. It's bad quality on YouTube. I guess it's the same quality here. What the frick? Why though? Nah, whatever. Whatever, okay. Alright. Okay. Alright, yeah, cool. It makes a lot of sense. So if S is changed back to 0, the circle will not change state because Q equals 1 feeds back into the first gate, causing P to remain 0. As shown. Note that the input are again S equals R equals 0, but the outputs are different than those with which we started. Thus, the circuit has two different stable states for a given set of inputs. If we now change R to 1, Q will become 0, and P will then change back to 1. If we, okay, change 0, 0, 0, R, 0. Okay, let's draw this out then. Let's draw these scenarios. All right, so again now, so we're coming from this state, so we can clearly see that we have 0 and 1. Wait, 0 and 1 are the current states of our P and our Q. So now let's assume that S equals 0 again. Let's assume this position that S is 0 and R is 0. 0, 0. For a NOR circuit is going to be P now equals 1, and we have 1, 0 is 0, Q equals 0, correct? Q equals 0. After we change this back, now the state, so that's essentially back to where so I'm missing something, that would remain 0, that would remain 1, obviously. Shit, okay. That's the thing I keep messing up is that's why we do it though. That's why we go through these scenarios. Because not is this preceding value 0, but it's like actually I should have drawn it better. But P equals 0. So, and Q equals 1. So 1, 0 is P equals 0. 0, 0 means that Q maintains 1. Okay. And so that is why it suggests that we have two different outputs for the same, or for two different outputs for the same pair of inputs. Okay, 0, 0. So now if we go through the scenario under which we change R to 1, let me draw that better. Boom. Our feedback loop. Boom. Okay, and P is 0. Q is 1. Now we're going to change S remains at 0. Let me draw that better. S remains at 0. R is now 1. Now with this combination, we have 0, 1 is still 0, but now we have 0, 1, which is 0. So now Q equals 0. Q equals 0. P remains at 0. Q equals 0. Okay. Yeah, that makes a lot of good sense. Okay. And now for this reason, we consider what do we consider S? Well, that's why it's called the set reset latch. Okay, the set reset latch. Right, because when S is high, set Q maintain that value though. What's the best way to describe it? Perhaps a book would put it into better words. If S is changed back to 0, the circle will not change state because Q equals 1 feeds back into the first gate, causing P to remain at 0. Blah, blah, blah. Blah, 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 blah. The circuit is said to have memory because its output depends not only on the present inputs but also on the past sequence of inputs. If we restrict the input so that R equals S equals 1 is not allowed, the stable states of the inputs P and Q are always complements. That is, P equals the complement of Q. To emphasize the symmetry between the operation of the two gates, the circuit is often drawn in cross-coupled form, which I'll draw. As shown if an input S equals 1 sets the output to Q equals 1, and an input R equals 1 reset. Okay, so an input S equals 1 sets the output to Q equals 1, and an input R equals 1 resets the output to Q equals 0. When used with the restriction that R and S cannot be 1 simultaneously, the circuit is commonly referred to as a set-reset SR latch and given the symbol shown in figure 11.5. Note that although Q comes out of the NOR gate with the R input, the standard SR latch symbol has Q directly above the S input. So, we just essentially, we derived a component which has memory. Okay? So that's the whole reason for this. That's the whole basis for what we're studying is, computer components. And now we just derived memory. So we can go ahead and implement this into a computer, into a circuit, and we can do a lot of great things, as you have already seen and witnessed before, right? You've seen the computing, you've seen what computers are capable of, and the incredible advancement it's brought to mankind. So now let's draw what it described as given the symbol shown. Note that although Q comes blah blah blah, shut up, cross-coupled. Let's draw the cross-coupled form. It looks more like this. Let's see, give me a little more space here. Kind of moving the mic further away, but I think the sound quality is still maintained. Check. Grrr, bow. Yeah, that's okay. Alright, so it's gonna look like we have our NOR gates, which is just an inverted OR gate. Okay, that's what the circle symbol indicates, is an inversion. How interesting. We come here, we go here, and we're going to do like this. Again, we come here, come here, we're going to go like that. Okay, now this is our R, and this is our S. Beautiful. Okay. And this is our complemented Q, and this is our Q. So essentially that's P, right? Because it specified that P and Q are always complements. That is P equals Q. So essentially that's P, right? Between the operations, blah 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 blah. SR latch. That's our SR latch, and then we can draw it as more of an abstraction, just like this. Just as like a block diagram. R, S, and Q, Q. And we'll notice that our, wait, what the fuck? That's kind of annoying. Just the way that it changed our complement to be above our S, and then now our function value, not the complement itself, but our original function value is above S. That's pretty annoying notation, how it's just changed like this. But whatever. Improper SR latch operation. Well, when they're both 1, is that what's happening here? I'm not really sure, but whatever. Timing diagram for SR latch, a timing diagram. Okay, let's go ahead and draw this out. I'm not going to do it for every component that we study, but oh man, kind of got a lot going on here. Gated latches. How many sections are in this chapter? Yikes. Let's see, let's see, let's see, let's see. No fucking way. Holy shit, there's 9 sections in this chapter. Oh man, cooked. Alright. Pretty cooked if you ask me. Oh man, I didn't record. Oh well, right? Shit, I probably should record. Time is it? 7:58. Man, I should have recorded, right? Because I want to post this elsewhere. Guess I can start recording now. Or should I go gym and then record? It's been like 45 minutes. Yeah, perhaps. Yeah. Alright. I will be back. Here, let's, yeah, alright. I'll be back. I'm going to go gym, and we're going to continue the stream once I get back, because I have a lot of studying that needs to get done, and we're really going to put our nose to the grindstone and get it done. Alright, we're going to work out these problems. We're going to learn more about more latches. Like, I know that there's the D latch, SR latch, D latch, T? No, maybe not. But anyways, and then our flip-flops, which are going to be the D flip-flop made of the D latches, and then the SR flip-flop, you know, as you can imagine, made of the SR latches. So we're going to get into all of that, and indeed soon. I'll probably be at the gym for like maybe 2 hours. I honestly need to be a little more particular about my time there. But I'll be back. Alright, I'll be back.